This is Saxon, Algebra 1, simplifying complex fractions, and we're going to work, this is lesson 92 by the way, we're going to be working with complex fractions on this lesson. I think you'll find that complex fractions are very easy if you treat them just like you would any other fraction. However, let me take just a moment and remind you what the word complex means. Complex means that it has a variable in the denominator. So these have variables in the denominator. I'm going to go ahead and just start with just a refresher of what a fraction is and why, even though that's very basic. So I have 1/2. That really is saying 1 divided by 2. And we've already done this. We remember this. But we also have this one here where we say 1/2 divided by 1/2. This is a fraction divided by a fraction. And in the younger grades, you memorized ways to do this, and you said, when you divide, you flip the second one, or you had little sayings that you would use for this. It doesn't really make a difference. However, you remember that you take the reciprocal function, right? So you say 1/2 divided by 1/2 is the same thing as 1/2 times 2/1, and you're flipping the second fraction. Now, that same idea is done for complex fractions. So I've got all variables in here, AB over CD. So what I'm really saying is the fraction AB is being divided by the fraction CD. When I have two sets of denominators here, and they're in a fraction, and a lot of students get excited and say, oh, I don't know what to do here. But really, we're going to take this logically and say, this fraction is being divided by this fraction. Just like 1 was divided by 2, we're going to say this one is divided by this one, so we just flip the second one, right? Or we put it up here first. We say AB is divided by CD. And then we could say, well, if we have a fraction divided by a fraction, we flip the second one, making it D over C, and multiply it out. Now, let's talk about why we do that, or why that we can do that. And that's because of a very special version of the number 1. Remember that 1 is the identity function for multiplication. Meaning if I multiply something by the number 1, I don't change its value. 3 times 1 is still 3. 6 times 1 is still 6. So it's an identity function, and any time I have a number divided by itself, it equals 1. So any real number. So when I'm working with these, and I look at it, I realize that I can multiply, just like when I'm finding a common denominator, I can multiply by a number as long as I do the top and the bottom, the numerator and the denominator, by the same value. I am not changing the fraction because that same value would have reduced to 1 anyway. So look at this here, and I say AB divided by CD. Well, what if I took and I multiplied the denominator by D over C? That would give me CD over CD, which is going to cancel out to just 1, right? But if I did that on the bottom, I have to do that on top. So DC over DC is just a very special value of the number 1. And how I chose to use that was I took the reciprocal of the denominator and multiplied it by both the denominator and the numerator, making it a multiplication by 1. When I do this, I end up with AD over BC over CD over CD. CD over CD cancels. That leaves me AD over BC. Now let's apply this to a couple examples. They gave me the example of AM over N. This is example 92.2, over X over MN. Now, I need to figure out what to multiply this by. On this one, I just flip the the denominator, right, and multiply by it, and that's all I'm going to do here, is I'm going to say, what would I multiply this to cancel it? Well, if I could have the perfect situation, I would multiply it by MN over X, because the X's would cancel, the MN's would cancel. But in order to do so, I need to make it a value of 1 by putting that in the numerator value as well. Now when I go ahead and do this, these are going to cancel, and I'm going to get AM times M, which is M squared, times N, times NX, which is NX. I recognize at the point here that I have an N in both the numerator and the denominator, and these can cancel out. That's going to give me AM squared over X. These are very simple to work with as long as you follow the rules of algebra, which is I can multiply by 1 without changing the value. These are just special values of the number 1. Now, look at example 92.3. Here I have an addition in the bottom here, and I have to just treat this the same way, except here's a fraction, a complex fraction, divided by a complex fraction. And I'm going to find the reciprocal of the denominator, right? Multiply it by the denominator and the numerator. The 9's are going to cancel, the x plus 2's are going to cancel, but what that's going to give me is a 3x times x plus 2 and a 6x plus 12 times a 9. And I put the parentheses in there because I have to make sure that I'm actually distributing, because it's not 9 right here times only 6x, it's 9 times 6x plus 12. So I put the parentheses on there. In fact, I could have used both of these terms in parentheses like this if it makes more sense, but I don't have to. But this allows me to realize that this is the first term, here's the second term, and that's what I'm multiplying them by, right? By just putting them close. Now, once I get to this point, I realize that these look like I might have something that would factor out. So I take the 6x plus 12 and I say, what's the biggest number that can come out of both 6x and 12? And that is 6. I pull that out of the front. When I do so, I have a 9 out there already. 9 times 6 is 54. Now I have an x plus 2 and an x plus 2. These here can now cancel because remember that division, its opposite operation is multiplication. And so when I can say the opposite, I have those on top, is that they're going to cancel out. Now, that leaves me with 3x over 54. 3 goes into 54 18 times. That leaves me with 1 on the numerator and 18 on the denominator. The x carries over and I have x over 18. Now, if you need to slow this down and watch it again, that's okay, but we're going to go ahead and move on to example 92.4. Now, this one is a little bit different, and this is probably the hang-up point for a lot of students, because up to this point, these are the same thing we've been doing with real numbers. These are just variables. Where we're adding in something here is all of a sudden I have a complex number that is not all one fraction. I can't take the reciprocal of this because there isn't a reciprocal of a non-fraction when it's not been added together yet. So the easiest way to do these is to add these up. Now I'm just going to pretend I only have that. And if I said to most Algebra 1 students, including you, hey, can you add that denominator up? And most of you can, realizing that you would have to have a common denominator, and the common denominator is x. So what would you multiply this by to get x? Well, x over x, right? And when you do so, you'll get x over x minus 1 over x. Now I can put them together, x minus 1 over x. Notice that my numerator just followed along. It just jumped along with us. At this point, we realize that now I have a fraction under a fraction, which means I can now take the reciprocal, there's the x over x minus 1, that's going to cancel this out, and realize that that number right there is going to cancel the denominator, but if I'm going to make it 1, that's why I put the big parentheses on there, x over x minus 1 divided by x over x minus 1, doesn't matter what x is, it's going to give me everything canceled out because it's a value of 1, and that's what allows me to do this. So now I'm going to say 1 times x, that gives me x, x times x minus 1, I'm just going to write them close, right, like I do in multiplication. Then I realize, oh wait, I have an x in the numerator and the denominator, I can cancel those out. It's not 0 though, because x divided by x is 1, and so I'm left with a 1 here over x minus 1. This is more just bookkeeping than it is math. It's keeping up with every little piece, not breaking any rules, allowing it to just work its way through, multiplying by very fancy versions of the number 1. And that's how you simplify complex fractions.